In this video, we'll work on the questions for homework number 11. Let's take a look at the first topic on conversions with dimensional analysis. For this lesson, Delta Math will provide you with a conversion table, but on the Regents exam, you'll find it on the reference sheet. So let's take a look at this question here. An object is moving at a speed of 350 feet per hour. Express this speed in yards per second. Round your answer to the nearest hundredth. So if you're reading carefully, you'll notice that you're probably going to get an answer with a really long decimal, and they want you to round to the nearest hundredth. So the first thing is you have to write down the first ratio that they provided you, which is 350 feet per hour. So that's 1 hour down in the denominator. And we're going to multiply by one or more other ratios that we find down here in the table to help us to convert to yards per second. So there are two different types of measurements here. There's the feet and the yards, and then there's the time, the hours and the seconds. And you have to deal with them each separately. So the first thing you need to do is concentrate on turning feet into yards, and then after that, you concentrate on turning hours into seconds. So let's look in our chart here and see if we can find any information about feet and yards. And I see here one single ratio. So 1 yard is equal to 3 feet. But you could also use this ratio in the reverse order. 3 feet is equal to 1 yard. Both of these are an appropriate representation of this fact. Now, which way you use the ratio depends on how you want to convert your units. So if I have feet in the numerator, right, on the top here, if I have feet in the numerator, then that means I need a ratio that has feet in the denominator, because that's the only way to make the feet unit disappear. So that means I'm going to use this representation. So 1 yard is 3 feet. All right, I've accomplished my transition there for yards, so now I'm going to focus on the time. I'm going to look here in my time chart to see if I notice any facts about hours and seconds. So here's hours, here's seconds, and that's it. So there's no direct conversion from hours to seconds in this chart, but I can go from hours to minutes. So 1 hour is 60 minutes, or 60 minutes is 1 hour. So I have to decide which ratio I want to use. So I have hours in the denominator, so I want hours in the numerator. That would be this one here. So 1 hour is 60 minutes. So now my hours have disappeared and my minutes are there, and now I need to convert again. So this time I need to multiply by something that has minutes in the numerator and seconds in the denominator. So I need some type of fact here in my chart that has to do with minutes and seconds. You see that here? I have a ratio with minutes and seconds, and that would be this fact here. 1 minute for 60 seconds, and minutes on top, seconds on bottom. That's exactly what I need. So now I have the right units in the numerator and denominator, and now I have one really large math problem here. So let's take our calculators out. Okay, I've got my calculator over here on the right, and I'm going to make one giant fraction, and I'm put all of the math from my numerator and all of the math from my denominator. So let's see, my numerator has 350, and then it has times 1, times 1, times 1. So I could write that, or I don't have to. Timesing by 1 doesn't do anything, but I'll write it just so that you can see that you can just copy exactly what's on your paper right there into the numerator. 350 times 1 times 1 times 1. And then I have in the denominator 1 times 3. So again, I don't have to write the times 1, but I will, just so that it's a direct translation. And then times 60, and then times 60 again. So let me make this a little bit bigger so you can see. In case you can't see it, there we go. So 350 times 1 times 1 times 1, 1 times 3, yep. So I'm going to go ahead and press enter. and I get 7 over 216. So I can either do that math myself, 7 divided by 216, and I can get that decimal answer, or I can use the math button and say take that fraction, choose number 2, and turn it into a decimal. It's going to take my answer from the previous line and turn it into a decimal for me. I did that using the math button. And they told us to round to nearest hundredth, so the 3 is in the hundredths place. The number next to it is not 5 or higher, so 0.03 will be my solution. So down here, I'm going to write 0.03 yards per second and submit. Excellent. Let's try another one. Water flows through a pipe at a rate of 290 gallons per day. Express this rate of flow in cubic feet per hour. Round your answer to the nearest hundredth again. All right, let's take a look here. First, we have to write our rate, 290 gallons per 1 day. And I know I'm going to multiply by some other rate that I find in this chart, but what I want to do over here is I want to turn it into cubic meter, so I can either use this abbreviation, cubic feet. I can use cubic feet, or I can use something like this, feet cubed. I think I'll use feet cubed because it's a little shorter. And we want per hour. All right. So we can only deal with one unit at a time. We can either do the volume or we can do the time. The volume is gallons, the time is day. So why don't we deal with the gallons first over here? Looking for a way to get gallons, so I need some type of ratio that has gallons in it. This one has gallons in it. This one has gallons in it. This one has gallons in it. So I see a couple of things that have gallons in it. So let's see. Now let's see if we can find cubic feet. So this is cubic feet. Oh, that's perfect. I want to go from gallons to cubic feet. So this is the winner. Awesome. All right, let's take a look. That's going to be the one we're going to use. So we have 1 cubic foot per 7.481 gallons. And don't forget, you could rewrite your ratio the other way, but I don't think we need to because we want gallons on the bottom. And this one has that. So we're going to put 1 cubic foot in the numerator and 7.481 in the denominator. All right, so we've accomplished the first change using this rate. And now let's convert the time. So we have days and we want hours. So let's see what we've got here. This is day. Oh, days to hours. That's a fast one. So we have 1 day is 24 hours. And we want days in the numerator, right? That's how it cancels out. And this rate does have days in the numerator. And this is a fast one. So get your calculator out. Turn it on. Let's see, clear out this old math. And we'll type one giant fraction here. And we had 290 times 1 times 1. And then in the denominator we have 1 times 7.481 times 24. And they want us to round to nearest hundredth. So the 1 is in the hundredths place, but the number after it is 5 or higher. So that's 1.62. So here on our answer screen, we're going to type 1.62 cubic feet per hour. All right, let's try one last question. This one says, water flows through a pipe at 830 cups every 3.5 weeks. Express this rate of flow in liters per day, round to nearest hundredth. All right, first things first, set up your first rate here, 830 cups every 3.5 weeks. Then over here on the right-hand side, we write down what we want, liters per day. And you start by converting one unit at a time. So let's see if we know anything about cups and liters. So let's see here. This one has cups. This one has cups. that's it for cups. So I have to use one of these. And none of these will get me to liters. So let's see if I can find anything with liters in it so I know where I'm trying to go. So we have liters with milliliters. We have liters with gallons. So I can go to ounces, or I can go to pints. Go to ounces or pints. Where else? Oh, this one, I can get to gallons. Okay, so if I can get to gallons, then I can get to liters down here, I see. If I can get to gallons, I can get to liters. So let's see if I can get ounces to gallons or pints to gallons. All right, well, I'm going to start with this one. I've got 2 cups per 1 pint. 2 cups, 1 pint, or 1 pint, 2 cups. So I want this one because I need cups in the denominator. So 1 pint, 2 cups. There goes my cups. Okay. So now I need to change my cups. I'm sorry. I need to change my pints. So pints can go to quarts. And then quarts can go to gallons, right? Pints to quarts, quarts to gallons. So there we have it. So first I'm going to use this one. 1 quart is 2 pints. 1 quart, 2 pints. And there we have our pints crossing off. And now I'm going to move to this one. 1 gallon. 1 gallon is 4 quarts. And there goes my quarts. And now I can use this one down here. 1 gallon is 3.758 liters. 1 gallon is 3.785 liters. Or 3.785 liters is 1 gallon, right? So let's see, what do I need? I need gallons in the denominator. So that's this one here. 3.785, and now I have my liters per 1 gallon. Okay. Gallon and gallon. Woo! I'm going to need to squish this a little bit. So I'm going to shrink it down a little bit. There we go. Alright, so I've done my liters. Now I need to go with my weeks to days. So I don't need any of this anymore. I don't need any of that. I need weeks and days. Oh, here we go. 1 week is 7 days. So I've got weeks on the bottom. That means I need weeks on the top. So weeks and days. 1 week, 7 days. All right, I've got my units. Now I need to get my calculator out. Turn it on, clear out my old math, open a new fraction. All right, this is a lot. Let's see. 830 times 1 times 1 times 1. I'm going to skip those this time. And times 3.785. And then times 1 again. I'm going to skip that. The denominator is 3.5 times 2 times 2 again times 4 times 1 times 7. All right, round to nearest hundredth, it says. So 1 is in the hundredths place. The next number is not 5 or higher, so it's 8.01. 8.0. So let's type that in here. 8.01. All right. Now we're going to move to the next topic here, which will be interpret linear equations in context multiple choice. All right, let's take a look at this question. Amadou is preheating his oven before using it to bake. Amadou wants to predict the final temperature after X minutes. He wrote the equation y equals 69 plus 45x, where y represents the final temperature in degrees Fahrenheit. What could the number 45 in Amadou's equation represent? All right, this is explaining meaning in context. So let's take a look here. We have, what could 45 represent? Well, 45 in this linear function is the rate of change. And a rate of change is known as the delta y over the delta x. And y represents, well, delta means change in the final temperature, change in degrees Fahrenheit. And x represents minutes, so the change in minutes. So it seems like we're going to add 45 here. So let me erase this part and fill in the number 45 over 1. So that means that the change in Fahrenheit will be 45 degrees every 1 minute. The change in Fahrenheit is going to be per minute. So I can choose that here, the change in degrees Fahrenheit for every change in 1 minute. And now we can submit. All right, let's take a look at the next one. Evan's math teacher finds that there's roughly a linear relationship between the amount of time students spend on their homework and their weekly quiz scores. This relationship can be represented by the equation y equals 68 plus 6.4x, where y represents the expected quiz score and x represents the hours spent on homework. What could the number of 68 represent in this equation? Well, when we have a linear equation, the coefficient of x is the rate of change, right, ROC, but this number is known as the initial value. Initial value. So it looks like 68 will represent a starting amount or an initial value. So let's take a look at our responses here. A student's expected quiz score if they spent 74.4 hours on their homework. A student's expected quiz score if they spent no time on their homework. A change in expected quiz score for every additional 1 hour students spend on their homework, or how many hours a student spends studying all year. Well, if we were to graph this, and x is the hours spent, and y is the score, and we have a 68 as our initial value, and then the score goes up 6.4 for every hour that you study. So that means that 68 is your initial score, or your score if you study for 0 hours. That's what that means. So it's not that they've worked for 74 hours. It's not the change in their score. And it's not how many hours they spend studying. It's what they would get if they spent no time studying. So we're going to choose this one here because it's an initial value. All right, last one. At the beginning of spring, Nichelle planted a small sunflower in her backyard. The sunflower's height in inches h after W weeks is given by the equation h equals 2.25W plus 20. What could the number 20 represent in this situation? Again, this is a b value, or an initial value. Right? It's the amount that you would have if the weeks was 0. If the weeks were 0, you would have a height of 20 inches, right? Because they're measuring in inches. So it's the initial value of the height. So is it the final height? No. Is it the sunflower's height when it was planted initially? This looks right. Let's keep reading. The change in the, no, change is a rate of change. The sunflower's height after 1 week? No, because it's the initial height. So this one is the winner here, and that's what we'll select. All right, let's go back and take a look at the third topic. Write an expression in context. mx plus b. That's how they want the expression written in linear form. All right, at the beginning of a snowstorm, Abigail had 12 inches of snow on her lawn. So we got some information here. At the beginning, right? At the beginning, she had 12 inches of snow. So that's the initial value. That's the b value. The snow then began to fall at a rate of 0.5 inches per hour. Assuming no snow was melting, how much snow would Abigail have on her lawn 5 hours after the snow began to fall? How much snow would Abigail have on her lawn after a random hour of snow falling? All right, so if she has 12 at the beginning, and then it's 1.5 inches for 5 hours, then that will give me the answer here. And if it's 12 inches to begin, and it's ½ an inch every hour, but we don't know how long it snows for, then that will be the answer for there. So I'm going to type that in here, 12 plus 0.5t. And then up here, I'm going to use my calculator to compute that math. Let's see what we get. So 12 plus 0.5 times 5. So 14.5 inches is what I will put there. All right, let's take a look at the next question. Jeriel is driving to a concert and needs to pay for parking. There is an automatic fee of $8, so that's your B value. Your initial value is $8 just to enter the parking lot. And when he leaves the lot, he will have to pay an additional $3 for every hour. $3 for every hour that he had his car in the lot. How much total money would Jeriel have to pay for the parking if he left his car in the lot for 3 hours? Well, T is the equation or the expression for this part. And if we know that he will be there for 3 hours, then that will be the answer for this part. So we can type in our expression here first. 8 plus $3 per hour, and then 8 plus 9, which is 17. You can use a calculator if you need to. All right, I think you're picking up on that one. So let's go back and try the next one of interpreting it. So they're going to give you some data here. There's roughly a linear relationship between the length of someone's femur, that's here, oops, sorry. The length of someone's femur, that's the length of the bone in your thigh, that's where your femur is, and your expected height. So what does the slope of the graph represent? Well, a slope is a change in y over a change in x. So as long as you can read the x and y axes, you can determine the labels that go here. So the axis for the y is change in expected height per change in femur length. All right, so all I'm doing is just copying these labels here. So the change in expected height over the change in the femur length. So let's go ahead and see what our choices are. So let me erase this, and so we can read. All right, the expected height for someone with a femur of 55 centimeters. Well, no, they didn't tell us any details about numbers, so this is definitely not true because it has nothing to do with just the slope in general. How about this one down here? The change in expected femur length. Well, what's the first thing? Change in expected height. So that's out. Change in expected height. Okay, we're good. For every, that's what this bar means, 1 additional centimeter of femur length. All right. Or the femur length for someone with an expected height of 55 centimeters. Nope, they didn't mention 55. So we found our winner because the slope is per 1. Slope is per 1. All right, let's try this again with the next problem. Robert is ordering a taxi from an online taxi service. He has to pay a flat charge just to order the taxi, and then he has to pay per mile, depending on how far he travels, as is represented in the linear graph below. What does the y-intercept of the graph represent? So the y-intercept is this point here, and a y-intercept is an initial value, or a starting fee, right? An initial value or a starting fee. So it looks like the y-intercept is 450, and that must be the flat charge just to order the taxi. So let's take a look at our multiple choices down here. The charge in the total cost for every 1 additional mile? Nope. The total charge of $650? Nope. The initial charge for using the taxi? Yes. Submit our answer. And one last problem. Dianellis is driving on a long road trip. She created the graph below to represent the gallons of gas left in her tank, right? So the more you drive, the less gas you have. What does the y-intercept of the graph represent? So it looks like the y-intercept is 9.5, and that is her initial value. And the initial value is gas in tank. So she has 9.5 gallons when she starts her road trip. Let's take a look at the choices. The number of gallons of gas initially in the tank? Yes. 9.05 gallons of gas in the tank after 1 hour? Nope, it's after 0 hours. How long it takes Dianellis to run out of gas? Nope, that's somewhere down here, off the grid. The change in the number of gallons of gas in the tank for every 1 additional hour? Nope, that's the rate. All right, let's go back and take a look at our last topic here for making equations, making tables and equations given a situation. So Caroline accepted a new job at a company with a contract guaranteeing annual raises. Caroline will get a raise of $3,000 every year and has a starting salary of $55,000. So that goes right here. Initially, she gets $55,000. I'll make a table of values and then write an equation S in terms of N for representing Caroline's salary after working N years. So what happens every time she works for a year? She gets $3,000 more. So 55,000 plus 3 is 58,000. And then plus 3 is 6,100. Oh, no, 61,000, sorry. And then plus 3 more thousand is 64,000. And now we can write our equation. So the salary she earns is $55,000 initially plus 3,000 per year. And they're calling that N, the number of years. Click Submit. Again, you'll be told in the story here the initial value. So Hannah was given a box of assorted chocolates. Each night Hannah treated herself to some chocolates. There were originally 24 in the box, so we start with 24. And she ate 3 chocolates per night. So then 21, and you take away, and 18, oops, 18, and then take away 3 more, 15. And since you know you're starting with 24, you should put the 24 first. And you know you're subtracting 3 chocolates each time you eat, right, in terms of T. So there we go. So we need a T here. Submit your answer, and you're all set. Good luck.